Okay, so this is proof by mathematical induction. So we're going to have case 1 and case 2. So here's the first part. So this is what we're going to do. We're going to show, here are the steps for math induction proofs. So first off, we're going to show that it's true for the A. So whatever number they're starting at, A being bigger than 1. Then, or in this, A could be bigger than 1, I mean, wherever it starts at. Like down here, N is bigger than or equal to 1. So this would be our A. So we're going to show it's true for the first number. Then step 2 is assuming it's true for the other k of them. So that's the inductive hypothesis. So we're assuming true. And then we show true for the k plus 1. So we use that if this is true, then the k plus first is true. So I use this assumed statement to prove this, and then it works. Okay, so here we go. So here's an example. So this would be your question. So use mathematical induction to prove that 1 plus 2 plus all the way up to n is equal to n times n plus 1 divided by 2. And that's for all n's bigger than or equal to 1. And I think I did explain this to you last year when we did this. I think we were together at that point. This was Gauss. He was being a bad little boy in class. And so his teacher said, okay, you go in the corner and you add up the numbers 1 to 100. And that's going to keep you busy for a while. And Gauss thought, I'm going to go add up the numbers 1 to 100 backwards. And then I will add up each of the columns. And each of the columns you can see would be 101. And how many 101s would I have? 100 of them. And that's twice the sum. There it is. So adding up the numbers 1 to 100. So summation up to, anyway, so I'm not going to worry about the notation. Add up the numbers 1 to n, so you take n times n plus 1 divided by 2. That's what this is, n times n plus 1 divided by 2. So, kind of a fun story. So let's go prove it. So first we're going to show it's true for 1. So if I plug in n equal 1, so I get 1 from the left-hand side, and from the right-hand side, if I plug in n equal 1, I get 1 times 1 plus 1 over 2. So I just went really slow so you could see, oh, look at that. I get 2 over 2. That's 1. Okay, check. It works. Okay, so then we say I'm going to assume it's true for k. So you just literally put it up to n equal k, and you put in n equal k. So this is something we will be using in our showing it's true. Whoops, gotta make the box. So this, again, we're going to be using this. So that's the deal with induction. You're going to have to use this. So remember that. So now we're going to go prove that it's true for k plus 1. So first off, as I plug in k plus 1 into my original statement. So I go up to past k, right? So that's important to write down k, and then the next term, which is k plus 1. Then on the right-hand side, I'm plugging in k plus 1 everywhere there's an n. So here's the first k plus 1 where there's n. Then I have n, so I'm going to put in k plus 1 plus 1. So I went really slow so you can see it. So simplifying this right-hand side, you get k plus 1 times k plus 2 over 2. Okay, so this equals this. Okay, so the deal with induction is you're going to substitute in, this is called the inductive step, the assume step. So this first k of them, right, the first k terms, I'm going to take those out. So I'm just working on the left-hand side. Take those out and put in this. K times k plus 1 divided by 2. Okay, then I'm going to carry this along on the left-hand side. And then you don't work with both sides at the same time. You work one side to get it to the other side. So I'm looking at these two, and I'm thinking, let's make common denominators. So if I multiply this top and bottom by 2, I get to this. Put the 2 together, multiply this in, so I get 3k plus 1. And then factor that out. It's k plus 1 times k plus 2 over 2. Oh my goodness, there it is. That's it. I have it. All right, so let's go prove this one. So know that you could turn the video off and see how far you get on your own. Otherwise, you can just follow along. All right, so first off, I have to show true for n equal 1. So you just have to literally plug in 1. So I get 1 on the left-hand side, equal, and plug in 1 on this side, 1 squared. Check, 1 equals 1. Okay, so now you need to say, I'm assume true for n equal k. Okay, so I have to write out 1 plus 3 plus dot 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 plus 2k minus 1 equal k squared. So now I'm going to show true for n equal k plus 1. Okay, so I'm going to come down to the next line. So what you want to do is you want to make sure you write out the first k term. So 1 plus 3 plus, and here's the kth term. Whoops, shucks. I meant to write a 2. Okay, let me try that. A 2, k minus 1. So that's the kth term plus, right? That's putting in k into here. Now I want to put in k plus 1 into here. So I'm going to go super slow. So 2 times k plus 1 minus 1, right, equal k plus 1 squared. So I don't want to take any simplifying steps so you miss where I'm doing. So let's write this out again, the first k of them, 2k minus 1 plus, and let's see what happens in here. So I get 2k plus 2 minus 1. So 2k plus 1 is what's left over there, right? So equal k plus 1 squared. Okay, mathematical induction works that you want to substitute in your assume steps. So these steps, this right here, I want to substitute this in. So I'm taking these out and putting in k squared. Then carry along this 2k plus 1. Oops, don't need a parentheses there, do I? Equal k plus 1 squared. Oh my goodness, is it true? Oh, sorry, it's a messy plus sign. Is this true? Is this k plus 1 squared? It is. Pretty straightforward. We've got it.